Hello, everyone. I just made a video on basically a particle in an infinite well. So that's basically a well that's, you can think of it as infinitely deep, or you can think of the depth as zero, but the walls are infinitely tall. That would be sort of one way to model something that has a huge force acting on it so that it can never, ever, ever exceed the x equals 0 and the x equal L range. So it stays right in between there. There's no way for it to escape. But in doing so, it gave me a quantization that's happening, and we can use that to model something. For instance, we can use it to model proton or neutron in an actual nucleus, because the nuclear force is so strong that it takes almost an infinite amount of energy. Not really, but it takes a lot of energy to get out. So that's one way of modeling it. You could also use it to model, say, an electron trapped in the space of an atom. That gives you another way. In this case, I'm wanting to actually calculate the probability densities from the wave function that we already derived. So let me start by sharing the screen to show you what we already derived. And you can see the video on infinitely deep well on my YouTube channel if you wish to review that, or if you haven't seen it already. So what we have here is a potential that starts at x equals 0, being in fact infinitely high. And then from 0 to L, it's 0, and then of course it's infinitely high at x equals L as well. So it's a piecewise potential. This is the general Schrodinger equation for one dimension. It's a second derivative in position, and that's supposed to be a 2 there. Hopefully everybody can see that. I know I'm having a hard time seeing it with my wonderful old age eyesight. So that's a 2 there. What we found first, by solving this, we found that K had to be equal to the square root of 2me over h bar squared, where h bar is, of course, h over 2 pi. But that was just a condition that had to be met for the actual wave function to fit within the range that we're dealing with, and so on and so forth. But then we had to use the boundary conditions, which is normally that the wave function itself is continuous and the first derivative of the wave function is continuous. In this case, it just applied to psi of 0 equaling 0 and psi of L equaling 0. The psi of 0 equaling 0 took our wave function, which was supposed to be a sine kx plus b cosine kx, and just made the b equal to 0. So we got just a times the sine of kx. But when we implemented the psi of L equals 0, that forced this k to be n times pi over L, because basically for n equal 1, you get some pi at L. So you get some pi for the argument of sine, and of course sine is 0 at all pi's, pi 1, 1 pi, 2 pi, 3 pi, 4 pi. So n is actually equal to 1, 2, 3, on so on and so forth. Now that did everything except for evaluate a, but then we use the normalization condition, which says that if you integrate the wave function, which is essentially 0 from negative infinity to here and 0 from L to positive infinity, if you integrate it from negative infinity to positive infinity, you should get 1. So that basically became the integral of psi star psi, which is, since none of this is imaginary, it's just a square of this, equaling to 1. In order to do that, I had to make the the coefficient equal to square root of 2 over L. Now, if I take the K, which is n pi over L, and set it equal to this, I can solve for the energy, and we found that the energy goes like the square of n. It's n squared h squared over 8ml squared. And if I call E1 just h squared over 8ml squared, then it's n squared times E1 for all the energies. So I'm not really too concerned about those energies right now. That's something I'm going to do a little later. But right now, what I'm going to do is graph the probability density. And in quantum mechanics, the probability density is just this quantity called psi star psi. So psi star of x times psi of x is the probability density. It's essentially the probability of finding, once you multiply it by dx, this is the probability of finding the particle between x and x plus dx. So in other words, when you multiply this by dx and then integrate it all, that should give you the probability over all space if you do it from negative infinity to positive infinity. What we're going to do is take and graph just this portion of the function to get some idea what it's shaped like. So this psi star of x times psi of x would generally be take all the i's and replace them with negative i's, and then multiply it by the case where you didn't do that, and you'll end up getting a real value, which is good because probabilities have to be real, and we call that real value just psi star, or psi squared, like that. So psi 1 squared is the special case of n equal 1. So I think you can see from here I get 2 over L times sine squared pi x over L. That's psi 1. And I'm going to do, when I go to graph this, I'm going to do L equal 1 for the graphing just to make it easier. And then psi 2 squared is again 2 over L times the sine squared 2 pi x over L. So you see it's going to happen more rapidly. In this case, you're only get half of a wavelength through. In this case, you're going to get a whole wavelength through. Psi 3 squared is going to be 2 over L times the sine squared of 3 pi x over L. And finally, I will say sine 4 squared is 2 over L times the sine squared 4 pi x over L. And I think you can tell, since I got a whole wavelength there, I'm going to get 2 wavelengths in there from here. These also correspond, of course, to E equals E1. E equals 2 squared times E1 would be 4E1. And this is E2, that's E1. E3 is going to be 9E1, and E4 is going to be equal to 16E1. Again, this is not anything I'm dealing with right now, but that in the future, what we know is if I take the energy of E2 minus E1, call it E21, that's E2 minus E1. If I set that equal to HC over lambda, that's the wavelength that would be emitted if a particle dropped from the n equal 2 state to the n equal 1 state. That's the wavelength of the photon that would be emitted. So that's a way you can go about calculating photons emitted when a particle contained in this well gives off or changes energy states. Of course, it also comes in handy when you can convert your H times C to, say, electron volts times nanometers, in which case it becomes 1,240 electron volts times nanometers. And we'll use that later as well. So my deal here is just to graph these and worry about this stuff later. But I was sort of pointing to where we're going. So let me share my screen. I'm going to use the wonderful product called Desmos and show you how we can actually graph this. So here's the Desmos product. I've actually got the range set from 0 to 1, which is really the relevant part. I've already made sure by clicking on this that I'm in radians. And I'm going to take and graph y equals, now remember I'm saying L is equal to 2, L is equal to 1, so 2 over 1 is just 2, so it's going to be 2, but I got to square it. Oh, actually, excuse me, it's already squared. So I got a 2 times the sine of parentheses, in this case it's pi. Oh, pi went to the wrong place. It's pi times x. And again, it's divided by L, but the L is in fact just 1. So I do a parenthesis there, but that's not sine squared. Generally, you put your exponent on sine here, but when I tried to do that earlier, Desmos stopped recognizing sine, so I'm just going to stick it out here instead. I probably did something wrong. I'm sure Desmos is smart enough to do it correctly. But notice that changed just a little bit. From there, let's get rid of this and see what happens. So you see what sine looks like? It's got a hump in the middle, but it's basically concave down the whole time. Whereas when I put this exponent of 2 on it. Now it's sort of concave up for a little bit on the left-hand side, then it becomes concave down, and then it becomes concave up again on the far right-hand side. But that's what the wave function looks like for n equal 1. Now, I want to graph the n equal 2 case, but I don't want it being on top of this. So what I'm going to do is I know the other one's going to come down because the coefficient, the amplitude is 2. I'm going to know it's going to come down to as low as 2 when it be squared, before it was squared, but because it's squared, it's all going to be positive, so the net should be a height of 4, but I should be able to put it right at 2 above it. So instead of saying y equals, I'm going to say y equals 2 plus, and I'm going to do the same thing now. So I'm going to say y equals, y equals 2 plus control V. Now in this case, instead of the pi, I got 2 times pi. So now you can see what the wave function looks like for n equal 2. For n equal 2, it's essentially 0 probability that you'll find it in the center, and it's the vast majority of the probabilities that you'll find it at the 0.25 mark or the 0.75 mark, whereas in the n equal 1 case, it was a probability that you're going to find it at at 0.5. Now, if I bump up another 2, I can actually fit in the other one. So in this case, I want to say y equals 4 plus, same function, except this time I put a 3 in front of the pi instead of a 4, instead of 2. So this will be n equal 3. And I do not know why it did not do that. Let's see again. So evidently it stopped plotting at n equal 3. Y equals 4 plus 2 sine 3 times pi times x. Now that we have that, let's erase the n equal 1 and see if it's just a matter of too much. Nope, I just had it turned off. Okay, so let me go back and type the y equals. So there's the n equal 1, there's the n equal 2, and there's the n equal 3. So now you see the largest probability are in 3 spots. So probably roughly a third would be a probability would be in the 1/3 mark, which would be 0.133 something at the 1/2 mark, and then again at this mark, which would be again about the 2/3 mark. So you see how that differs. Now I can do the y equals 6 plus the n equal 4 case. So y equals 6 plus control V, and now I'm going to slip a 4 in here. And you can see now the n equal 4 case has a high probability here, 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 and here, and essentially 0 at the quarter. So it really is in contradiction to what's going on for the n equal 2. The n equal 2, we had a high probability at 0.25 and 0.75. At n equal 4, we have essentially 0 probability at 0.75 and 0 probability at 0.25. Similarly, for n equal 3, we had n equal 3, you can see about 0.1666 was where a maximum probability was. There was another one, of course, around 0.5, and another one around 0.833, so 83 1/3% roughly. So that is the actual probability densities. If you wish to calculate the average value of x, I think you can tell from symmetry it's always going to be 1/2 no matter what the n is, because even this case, this one and this one's going to counterweight each other, so the center is going to be the right spot, even though you'll see it's about 50% chance of being between here and here. So, and 50% chance of being between here and here. So that leaves essentially 0 probability there. Now, if you wanted to actually calculate the probability or the average value of x, what I'd do is you take psi star x times psi and you integrate that, and that would give you the average value of x. Now, since psi is not imaginary, it doesn't really matter. And since x is not an operator, it's just a multiplier, it doesn't matter whether x is between the two or it's out in front. You can do it either way. So it's actually quite easy with this simple case of an infinite well. So that's what the psi squared looks like, and therefore the probabilities look like. Again, I've shifted them up by 2 and 4 and all that stuff just because I didn't want you to them to lay on top of each other. I wanted to be them above each other but not touching. So this is the n equal 1 case, what psi star psi looks like. This is n equal 2 psi star psi. This is n equal 3 psi star psi. This is n equal 4 psi star psi. Notice this is in fact basically at n equal 4, we ended up getting 2 whole wavelengths, but squared, which makes it like 4 wavelengths. So I guess that's it. Hope this helps you, and we'll call it a day.